Okay, well, I'm going to get started. We can have people jump in and join us as they show up, if they show up. Good job on your guys' test. If you didn't give it to me yet, then make sure you send it to me sometime today. So the part 2 of the take home. Here is our list. Where's our list? Here. I think this is it. Okay. Here is our list of dates and the rest of the calendar. We're going to wrap this up this week with an introduction to series. We're going to go fairly fast through the rest of the series. We could spend a lot of time here. In fact, you can take an entire class just on series, and we're not. We're going to spend a week. And so notice that I did 3, and then I'm going to do 4, most of it. And then I'm going to do 5 and 6 by talking about it and saying you guys can look at it some on your own. 7 is wrap it all up. So just like we found different ways to find integrals, we're going to find some new tools for deciding if a series converges or not. And we're going to look at the first couple of 2, 3 tools, and there's going to be more tools, and we're not going to do them all. So I'm going to just refer to them. And then we're going to try to do 7 without doing 5 and 6 officially. So we'll see how that goes. I don't know how much of 7 we'll be able to do because we won't have seen every one of the tools in our toolbox. Then we're going to go on and talk about something called power series, which is the most important series that we will consider, and wrap it up with Taylor polynomials. So we have 3 weeks left after this. The final is going to be at the regularly scheduled time. So for us, it was scheduled 8 to 10 on, I think that's Wednesday. I'll be happy to stay a little longer. Like I can stay till 11 and make it 3 hours instead of 2, but you should check with your final exam schedule. I want to make sure that I'm doing it at the right time so that you guys don't have an overlap or conflict or something like that. So if you do, and you notice that you're going to have one, and you want a little extra time, then let me know. We'll figure it out. We'll either start early or do something else. Okay. So if you're going to have a conflict and you can't stay a little late and you think you might want to, then let me know and we'll do what we got to do. Okay. There's the calendar. Questions about anything there? Okay. Well, looking good then. Also be on the lookout here, maybe as soon as I get time. The district decided that they're going to switch grading on classes from ABCD grading to credit, no credit grading. Essentially, they're going to give you the option to take a pass-fail if you want. But the way that they set it up, it's going to default to pass-fail, and you have to elect to take a letter grade. And so that's kind of the backwards way because you were expecting a letter grade at the start. My recommendation is, especially for the 3 of you, that you just take your letter grade because it's going to be more transferable. It's what you expected, blah, blah, blah. But if you want a P instead of an A, well, you can take one. But I will send out an announcement. And what I need from you is for you to just, it's going to be a little Google form, and you'll have to click the box that says, I want a letter grade, or I want a credit, no credit grade, right? And so you just click it, and then I'll have it recorded, then we can go from there. So look for that in the next couple of days. Other than that, I don't have any official announcements. So I think we can get started if you don't have any other questions. Okay, well, let's see how to do these. We already looked at these last week. Right? This is a sequence, and we're asking what is the limit of this sequence. So officially, it's an infinite sequence. We don't generally explicitly say that n is a natural number, right? We just use n, and it's sort of implied that it's a natural number. So if there's a question, then you ask for clarification if it's not clear from the conversation. So that makes it a sequence, and since it's going to infinity, we say it's an infinite sequence, and what we want to know is what's happening with the terms. So what you should do is maybe list a few, maybe graph them, see where they're going and guess, and then give some kind of stronger justification other than guess. In other words, maybe you would use some algebra, okay, or one of the tools that we talked about last week. So for me, what I would do, first of all, is I would list a few terms. And since I'm a big fan of not doing calculations on my own because I make errors, I would go to Desmos, although you can go anywhere you want, and I would put in this function that we're considering. And then I would say, okay, now check it out. Desmos thinks that n is a real number, right? That the independent variable is a set of real numbers. And so it graphs all of the real number points. Well, it doesn't. It graphs enough that these dots are close enough together that they look like they're continuous. But in fact, Desmos is actually just picking dots on the screen, pixel-sized dots on the screen, and it doesn't do every real number. There'd be infinitely many of them. So if you want to see just the dots, then what we want to graph are just dots. So we say, let maybe big N be the set of all of the maybe first, I don't know, 100, maybe that's too many, 50 integers. So N is now 1, 2, 3, 4, 5, 6, 7. It's an array of all those values. And then we say, just go ahead and graph the N versus the A sub N's. In other words, take 1, stick it in the function, get the output, put the dot. Take 2, stick it in the function, get the output, put the dot. And so this set of green dots is actually the sequence that we're interested in. And if you wanted to see a few values, of course, you could click on them, but that's a little bit annoying to have to click them all. And so if you wanted a table, you could add a table. See if I can make this work. I always get this mixed up. It seems like it doesn't play nice with lists in a table, so I'm going to do this sort of the old-fashioned way. 1, 2, 3, 4, 5, 6, 7, 8. And then for Y1, I'm just going to say, how about A of X sub 1? Okay, and so look at what we get. Here's a table of all the values, and of course, it's graphing those red dots that I've put in the table now. So if you just want to see what the list looks like, you can maybe make a table. So here's what you got: 4, 3.8, 4. It went down, then it went up. Okay, 4.15, 26, 35, 42, 48. Looks like it might be leveling off. And so then you would guess, looks like it's leveling off at 5. I think the limit is 5. Questions about how to use Desmos to get a picture of what's happening? I'm thinking this is a very valuable tool. Like, this is my go-to. I would do this every single time for every single problem in chapter 11. Okay, I would look at it first, just to make sure that I got it in my head straight about what's actually happening. And now you've got to prove, yes, you got to prove. You can't say it just looks like it's going to 5. You have to prove it's going to 5. But at least from the picture, you got a pretty good idea that it's heading there. Okay, so how do we prove it? We prove it a lot like what's going on in this picture. We notice that these green dots, the sequence that we're interested in, is following this red function. In other words, the values of the sequence are the values of the function at the integers. And this is a pretty big trick, okay? It basically says that we can consider the limit as x goes to infinity of 3 plus 5x squared over x plus x squared, where x is a real number. So in other words, these values, right, of the sequence are following this function, which means if we can figure out where this function goes, then we know where this sequence goes, and then we're done. This is an awesome trick because we already know how to find the limit of a function, right? We already have lots of tools for that. We already have lots of ways to do that. So I would say this is the strategy that you would use almost all the time. Now, there are some sequences whose formula is not defined for all of the real numbers, in which case you can't use this trick. One example might be if I want the limit as n goes to infinity of let's see, something good. How about n factorial over n to the n? So the factorial function is not defined for all real numbers. So we can't consider where does x factorial over x to the n go or x to the x go, because it's not real value. So for this one, that trick's not going to work. But for both of these up here, 1 and 2, it will work. And that's what we use. So how do we find this? When x goes to infinity, essentially all I'm asking is where's the horizontal asymptote, right? And you guys know how to find that. When the powers are the same in a rational polynomial, it's the quotient of the leading coefficients. So this goes to 5 over 1 or 5. I mean, that's the quick way. That's how we did it back in Math 150. Now, if you want to be a little bit more thorough, you could use the limit laws. You could explicitly state them all. But the easiest thing that we've said is divide by the highest power of the variable in the denominator. So divide top and bottom by x squared. You get 3 over x squared plus 5. You get what? 1 over x plus 1. And then you say, okay, the limit of a quotient of limits, limit of a sum is the sum of the limits, limit of this is what? As x goes to infinity. 3 over x squared.
0.
That goes to 0. This goes to 0. I'm left with 5 over 1. Okay, 5. All right, so this argument here that we made is an old argument back from first semester. And the trick that we used is that the values of our sequence follow the function. So that's a pretty nice way to do it. In other words, turn the new problem that we have from section 11.1 into a problem from, from years gone by, right? All right, so how do you do this one? Well, you might say the values of our sequence follow this function, and you might consider what happens when x goes to infinity of x sine 1 over x. And then you'd say, well, this goes to infinity. This goes to 1 over infinity goes to 0, and the sign of 0 sounds like it might be 0. So this is 0 times infinity. Well, if this gets to 0 first, then 0 times infinity would be 0. But if this gets to infinity faster than this gets to 0, then a big number times a small number is a big number. So this could go to infinity. In other words, this is an indeterminate form. Okay, and that should be screaming out L'Hopital. But L'Hopital's rule is only good when we have 0 over 0 or infinity over infinity. So we rewrite this a different way. We say, maybe we say the sine of 1 over x over 1 over x. In other words, divide top and bottom by x. Now the top is going to 0, the bottom is going to 0, so we have a true L'Hopital's rule. So we can see the quotient of their derivatives. How fast are they going to 0? Who's winning, the top or the bottom? So we take the derivative. I'm having some trouble taking the derivative. You guys could help. The sine of something, derivative of sine is what? Cosine? So we get cosine 1 over x times the derivative of 1 over x. I liked just memorizing that one. You know, remember when we memorized that so I don't have to use the power rule? That's always nice. And then what do we get down here? Well, that's 1 over x. So the derivative of 1 over x minus 1 over x squared, check it out, those cancel. So now the question is, where does cosine 1 over x go? And we need another one of our limit laws. It's the law that says the limit of a function is the function of the limit of the function, as long as the function's a continuous function. Well, that sounded weird. They probably wrote that more officially in the book. Essentially what they're saying is check out cosine. Is that a continuous function? Then we can rewrite this as the cosine of the limit as x goes to infinity of the 1 over x. In other words, just figure out where the 1 over x is going and then stick it into the cosine function because the cosine function is continuous. Now, you guys can say the cosine function is continuous because you proved it, right? But you can't do that in general. You would have to stop here and prove, right, that the cosine function really is continuous before you can do that. So be careful using this trick on functions that you haven't shown to be continuous. Or worse, try to use this trick on a function that isn't continuous by mistake and then have an error. Yeah. Okay, where does this go?
1.
No, close. Bottom's getting big.
Oh, I meant overall, but that's 0.
So, oh yeah, 1 overall, right on. The inside going to 0 now, yeah? 1 over something big goes to 0. Cosine of 0 is 1. So check this out. Here's the 11-2 part. This is the only new part that you learned last week. I want to know what happens when these are positive integer values, right? I want to know when the domain is the natural numbers. I just want to consider the sequence now. So what did I do? I just turned it back into a real valued function and did a problem from, I don't know where L'Hopital rule was, 3.7 or 3.8, somewhere back in there. Okay, so this is, again, an old problem. So the only thing we did in section 11 is said, when we get one like this, if it follows the function, then just figure out where the function is going. You already know how to do that. If you get one like this, okay, then you can't do that because, again, 1/2 factorial isn't defined. Well, that's kind of a lie. It's not defined for us yet. Okay, somewhere down the road we do define it, but it's not defined in sort of the way that we've been thinking. Okay, and so you can't use this trick. So how do you do this one? You say, well, look, 10 to the 10th is a heck of a lot bigger than 10 factorial. So I'm pretty sure the bottom's getting big really fast, which means I'm pretty sure this thing's going to 0. And then you could look in Desmos and confirm. Okay, so I'm pretty sure it's going to 0. Then you have to come up with a different trick. You have to come up with a proof that says it's going to 0. So we had a little theorem that was helpful, right, that we used instead of using the definition. The definition says somewhere out there, as n is going to infinity, somewhere out there there's a number beyond which I'm close enough to the limit. In other words, I stay within that limit of 0. I get closer than that number of 0 and I stay there. Okay, that number's hard to find. Okay, so instead we use a little theorem. Do you remember what it was? We say the function has to be, starts with an M, monotonic and starts with a B, bounded. If it's monotonic and bounded, then it has to converge. Now, just because we know it converges doesn't tell us where it converges to, but at least we know whether or not we should be hunting for this limit. So think about this. Monotonic means increasing or decreasing. Well, what's this function doing? And you say, I don't know, I got to look in Desmos. Okay, fine. So then you go off and you look in Desmos. So let's look in Desmos. We'll change it. N factorial over n to the n. Notice that Desmos knows what's going on with the real values. Uh-oh. We don't know what 1/2 to the factorial means, but Desmos seems to know what 1/2 factorial means. So you're going to have to hang in there. Okay, but for us, since we don't know what that means, we can't use that trick right now. So really, we should turn this off and just consider these dots. Where are they going? Sure looks to me like they're getting closer and closer to 0. In fact, they're getting closer to 0 really fast. Okay, so would you say decreasing? I would say decreasing, right? And bounded? Yeah, bounded above, it doesn't get any bigger than 1. And bounded below, it looks like it's bounded below by 0. So what you would have to do is prove this function's always decreasing. So to prove decreasing, we'd have to show, these two things, that a sub n plus 1 is less than or equal to a sub n, right? And we would have to show, that would be 1, right, decreasing. And 2, we would have to show that a sub n is greater than or equal to, well, greater than, I guess we could say, or equal to 0. Okay. In fact, if we want bounded, then we should show this. 0 is less than or equal to a sub n is less than or equal to 1. It should be shown that it's bounded on both sides. In which case we would know it converges, but I'm feeling like it's going to converge. Okay, so so that would be how you would use that theorem, and then you'd still have to figure out where it goes. I would suggest maybe that we could do a different, and then what it comes down to is you have to use an individual trick for each individual function, right? These are some general things that you can do, and then there are some kind of tricks that you can do. Whenever I get n factorials, I generally write them out. So I would do this one this way. N factorial is n times n minus 1, right, times n minus 2, times dot, 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 times 3, times 2, times 1, yeah? And n to the nth power is n times n times n times dot, 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 right? N times n times n. On the top, you would have n values, starting at n going down to 1. And at the bottom, you would have n n's, because that's what n to the n means. Now I'm feeling pretty good, because look at this. I can consider each one of these, because the limit of a product is the product of the limits. Then consider this quotient, and this quotient, and this quotient. Well, where's this one going? You say 0.
Could you switch it? Could you switch it over to the page so I can see?
Yes, sorry about that. Okay, so where does 1 over n go? It goes to 0, right? And then where does 2 over n go? It goes to 0. And this one goes to 0. And where does 1 over n go? This goes to 1. So what do I have? I've got 1 times 0 times 0 times 0, 0, 0, 0, 0, 0, 0. Well, that sounds to me like 0. And we would be done. Okay? So in general, when you're trying to prove the limit of a sequence, we often use this trick by considering all of the real values and seeing that our sequence follows the function. And then we use things that we already know to prove where the function's going. In the case where we can't use that trick, then we just do something special, right? We can use our monotonic bounded theorem to show that it converges or not. But after we showed that it has a limit, we still have to find it. And that generally involves a little bit of cleverness. Okay, now, of course, once you've seen the cleverness, like in this case, you can just do the same thing for a similar problem. That seems to work pretty good. Okay, questions? So then that begs the question to see if you guys understood what was happening there. Then you would try one on your own, and maybe you would try this one. N factorial over 2 to the n. And then you'd say, I don't know, where does that one go? And then you try it. And while you're trying it, I'm going to make the screen tiny again, sorry. Because for me, I'm kind of thinking, I look first. And I'm pretty sure this one's going where?
Positive infinity.
It looks like infinity. I'm saying diverges. What's going on? The top is getting bigger faster than the bottom. So this function is actually increasing. It's increasing and it's not bounded. So it doesn't have a limit. Okay, but how would you show it? You might do something similar. You might say this is the limit as n goes to infinity of, n times n times n times n over n over what's on the bottom. 2 times 2 times 2 times dot. Oops, I wrote the top wrong. N times n minus 1 times n minus 2 dot, right? 2, 1. Well, this fraction's 1/2. That's definitely small. And this fraction is 2 over 2, so that's 1. But look at all these other fractions. Aren't they all bigger than 1? So if I multiply together a bunch of numbers that are bigger than 1, I think I get bigger than 1. In fact, it's going up and up and up and up and up. Diverges. So again, using a similar trick seems to work pretty good in this case. All right, well, that's the recap. Any other problems from 11.1 that were bothering you from last week? I know maybe you didn't have as much time to focus on it because you were working on integrals. There should be some in the homework for you to try now, right? You see if you can finish up the ones from 11.1. It's going to be a good idea to get those done real quick because we're about to move on. And guess what? We need all that stuff from 11.1 to be able to do 11.2. Just like any good math class, right? It's my favorite part of Calc 2. You use everything you've ever learned in your whole life every day. Right? It's pretty cool. Okay, so here we go. I want to talk now about section 11.2. It's called series. Okay. And so first of all, we need to know what a series is. Hello, come on, come on. There it goes. A series, it turns out, is a sum of a sequence. And so what that says is you take all the terms in your sequence and you add them all together. So here's a nice sequence. 1, 2, 3, 4. I might ask you, what are the next 3 terms? What's the formula? Where's it going? Those are the kinds of questions I might ask. You would say the next terms are 5, 6, 7. A formula is a sub n is equal to n. And where is it going? The limit as n goes to infinity of a sub n equals, well, infinity, right? It diverges. Is that Carlos joining us? Good morning. Okay, so this is how the game goes. I give you a few terms. You give me a few more terms. Then you give me a formula. Then you tell me where it's going in the end. Okay, so now what I want to do is I want to take this sequence and I want to sum it up. So now I want to consider 1 plus 2 plus 3 plus 4 plus 5 plus dot, dot, dot. And I want to say, what's that doing? This is called a series, when I sum together the terms of a sequence. Now, of course, we could write that in shorthand notation like this. It's the sum I equals 1 to n of I. But it's not just n now. That would be if we went over here and we stopped at n, right? But we want to actually not stop at n. We want to keep going and consider what would happen if I added up infinitely many terms. So I changed the n to an infinity now. So we've seen the sum of a finite sequence before. We know how to add together the numbers from 1 to n. In fact, I'm pretty sure you have a formula for that, yes? What's this? The sum, I equals 1 to n of I. You'd say, you guys forgot Riemann sums already? You know, it feels like it's been like 100 years ago, but
It's, yeah, it's there, just missing the limit.
so what's going on? How do I do this? Let's use Gauss's trick. That's where you add them up forward and backwards, right? So you say 1 plus 2 plus 3. Notice that it's stopping at n. If I add them up backwards, n minus 1 plus n minus 2 plus dot, 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 down to 1, what would I get?
Oh, it's n times n plus 1 divided by 2.
Sure, check this out. You get n plus 1 for this sum, right? You get n plus 1 for this sum. You get n plus 1 for all these other sums too, don't you? And so how many of them are there? There's n of them. So you'd get n times n plus 1. And of course, that would add them up twice, forwards and backwards. So the true sum is n times n plus 1 over 2. Okay, we know what this is. That's awesome. And it took a little bit of a trick. What happens if you have a formula, or you suspect you found a formula, but you don't have a cool trick like Gauss used? What do you use?
Math induction.
You use math induction, exactly right. And I think we proved the squares and the cubes, and I don't know, you did one of those on a test for me a little while ago. Okay, so now look at the difference. Now what I want to do is, instead of adding up a finite sequence, I want to add up an infinite sequence. And of course, the easiest way to do this would just to say, well, I can't stick in an infinity. So what I'll do is I'll take the limit as n goes to infinity. So this is equal to the limit as n goes to infinity of the sum I equals 1 to n of I. So I say, well, what if I just add up, the first n i's, and then I let n get really big? Oh, that sounds like a pretty good thing to do. We can do that because we know that the sum of the first n i's is n times n plus 1 over 2. So what happens when n goes to infinity?
It looks like it just keeps getting bigger and bigger.
Yeah, it sure does. Infinity times infinity plus 1 over 2 sounds like infinity to me. So he would say it just keeps getting bigger. Obviously, if I'm adding up a bunch of positive integers and I add more onto my sum, it's going to keep getting bigger, especially if the thing that I'm adding is bigger than the last thing. I'm adding a bigger and bigger chunk onto the end of a sum. So it sounds like it's going to infinity. Okay, so how could we check? Well, of course, we can check the way I love to check. So what would you do? You'd share your screen again, probably, and go back to Desmos. And now you're saying, I want to, this is a pretty simple formula. It's just the integers. So you just say, those are the integers. That's a nice place to start. But of course, if you were doing homework problems, after a while, we might put something a little more complicated in there for the formula. And then we'd say, all right, these are the dots. Okay, this is the sequence. But now I don't want the sequence. What I want is the sum of the sequence. So let me stop sharing for just a minute. In other words, if I want to know where this sequence is going when I add it up, I'm going to consider the consider the sequence of what we call partial sums. Okay, so what we want to do is consider the sequence of partial sums. So it's a sequence now, and it's the partial sums. So we would take, if we're wondering where the sum I equals 1 to infinity of I goes, right? We're wondering where this goes. Why don't we just take, let me leave that there. Let me rewrite it this way. The limit as n goes to infinity of the sum I equals 1 to n of I. Consider this for individual values of n. In other words, what sum would I get if I just let n be 1? In other words, it's the sum not of all of them. We'll call this big S. We'll call this S sub 1. S sub 1 is what I get if I just add up one term. So what would you get? 1, yeah? Starts at 1. And so what would you get for the second partial sum? You get 1 plus 2, which is
3.
3. And then the third partial sum, you get 1 plus 2 plus 3. Sounds to me like you get 6, yes?
Mm-hmm.
So then what is the fourth partial sum? How about 10? And the fifth, how about 15? What about the nth partial sum? You even know that one. ... The nth partial sum is what? We just did it, although I've scrolled it off the screen.
Infinity.
Nope, the nth one.
Okay.
N times n plus 1
Over 2, you got it.
over
Oh,
2.
yeah.
Okay, so what we do is we say, if I want to know what the sum of infinitely many of these terms would be, I'm going to look at, well, what's the sum of the first one term, the first two terms, the first three terms, the first four terms? And I'm going to look at this sequence and I'm going to say, this sequence looks like 1, 3, 6, 10, 15. And in this case, I found a formula for the ... which is cool, because then I can just take the limit of that formula as n goes to infinity. This is going to be, of course, the challenge. If you can find this formula and you want to know where the sum goes when n gets big, you just let n get big and find this limit. So by looking just at these terms, even without finding this formula, we should be able to say, those look like they're getting bigger and bigger to me. I think it diverges. Does this make sense? Okay, I'm getting some nods.
I have a quick question, actually.
Yes?
So I was looking at the homework for 11.2, and there was a problem similar to this. And so they
Okay.
gave S sub n. And for some reason, the way I was thinking it would work wasn't the way it was working. I'm not sure why. So S sub n was 15 over negative 4 to the n.
Okay, so they said, I've got some partial sums, and it's 15 over
Negative 4 to the n.
negative 4, like this, to the n power?
Mm-hmm.
Okay,
So it was a table of from 1 to 10, and the first term was right.
okay,
And so basically what I did was I just set up that equation in the background of my calculator, and I
okay.
just plugged in the terms 1 through 10.
Yes, that
Now,
will give
the
you the
first
first
one
two partial sums. So you get
Okay.
minus 15 fourths, right? Then you get S sub 2. Well, what's that? That's what you get when you put a 2 in here. Because this is the formula for the partial sum, not the formula for the nth term. So
Okay.
S sub 2 is what? It's it looks like 15 over 16.
And that's where it started not being right. For some reason, it wasn't taking the answer. And I mean, if you're saying that's the way it should have worked, then I'll just go back and make sure I was doing everything right, make sure I was typing in everything right. But that was what was confusing.
I think that's what it's trying to say here. So let's put it back on Desmos and have a look at it. What we're saying is, these are the terms of my sequence now. But what you're saying is that they've given us a formula for the nth partial sum. So this is the formula for the nth partial sum. If we wanted to do that for our last problem, then we'd write this, right? These are where the sums are going. So here's the sums. Look at the sums getting bigger and bigger and bigger. Okay, but now what we have, I'll turn that off. Now what we have is 15 over minus 4 to the nth power. And so what we'll look at is where are the sums going? So if we graph n and the sum now, I'm confused why that's complaining. Oh, big S. Okay, then here are the partial sums. So look at what the partial sums are doing. They're alternating, right? Negative, positive, negative, positive, negative, positive. It looks to me like these sums are going where?
To 0.
It looks like they're going to 0 to me. Okay, and so the way that you would prove that, right, is you would say, take the limit as n goes to infinity of the partial sums. And you say, where is this going? Well, that's equal to the limit as n goes to infinity of 15 over what, minus 4 to the n. Guess you don't need those parentheses. So where's that going? I don't know, it looks like the bottom is alternating, right? So we need maybe a theorem to help us. Could we consider the limit as n goes to infinity of the absolute value of 15 over minus 4 to the n? If the absolute value of the terms go there, then the terms have to go there. Do you remember that little theorem? If they go to 0, this goes to 0, those go to 0. But that takes care of our negative sign. So then we'd say this is the limit. Of course, the absolute value of 15 is 15, and the absolute value of minus 1 is 1. So we get 15 over 4 to the n. Looks like the bottom's getting big, the top's staying the same. This goes to where? 0. Okay, so here's the deal. The one that we just considered, right here. If I add up the integers, 1 plus 2 plus 3 plus 4 plus 5, then it just gets bigger and bigger forever. Boring, yeah? It just diverges. So who cares? It doesn't do anything cool. So the question is, well, if I add up the terms of a sequence, do they ever do anything cool? And by cool, I guess I mean, does it ever go anywhere?
That's the NOS plug.
So let's look at another example. Let's do this one. Let's do the sum I equals 1 to infinity of 1 over 2 to the n. And say, I wonder where this is going if I add up all the terms of the sequence. Okay, so a bunch of things we should probably do here. I'm going to do them in Desmos because I always do, and it's always easier for me that way. And I might recommend that you try it because it might be easy for you. The question is, what do the terms look like? And the terms, right, look like 1 over 2 to the n. So the terms all look like this, 1 over 2 to the n. And if you want to make a picture of them, right, that's what the terms look like. So what do you got? You've got 1/2, 1/4, 1/8, 1/16. You with me? So what's going on with these terms? They're getting what?
Getting smaller.
Smaller. If I put in a positive number, then 2 to a positive number is a positive number, which means this number is always positive, which means 0 has got to be smaller than it, which means this sequence is bounded. It's getting smaller and bounded. Has a limit, doesn't it? And what's the limit?
0.
0. The terms are going to 0. Okay. So far, all we've done is section 11(1) type stuff. That's it. Now what we want to do is say, well, what if I add all these terms together? Okay. Well, maybe I should list a few so that you can see them. let's see if I can make a table so that you can see a few. So I would say, okay, put in 1, 2, 3, 4, 5, 6, 7. And what would the terms be? The terms would be a of x sub 1, right? A of x sub 1. So what do we got? A half, a quarter, an eighth, a 16th. And now what I want to know is, what if I add these terms together? Since I'm adding on more stuff, right? I'm adding on more stuff, I would expect that the sum keeps getting bigger. But what I'm adding on is getting smaller and smaller. So the question is, am I adding something that's getting small so fast that it doesn't make a difference? Or am I adding stuff on fast enough that the sum keeps accumulating and keeps getting bigger and bigger and bigger? Sounds like a race problem, like we've been talking about so far. So what we want to look at, if these are the terms, I'm going to spread them out a little bit so that we can see them. 0 to 1. Okay, so I just spread them out a little bit so we can see them coming down. Then the question is, what are the sums doing? Okay, so what we want to look at are the partial sums. So what we want to look at is the sum. We already used n, so I'm going to use I. I goes from 1 to n of a sub n. What that's saying is, add up the first n terms of my sequence a sub n. So when n is 1, let's get this out of here for a minute. When n is 1, s sub 1 should be what I get when I add one of those terms. In other words, 1/2. When n is 2, I should get 1/2, right? Whoops. I should get, why am I getting that? That's not what I expected. Is that what you expected? That's interesting. Oh, why? Because look at what I typed. A sub n, right? You don't want a sub n's. You want a sub i's, right? Add up the ith terms. That's looking better now. So what do I get? I get 1/2 plus 1/4, better known as 3/4. Is this making sense? Okay, now what do I get if s is 3? I get 1/2 plus 1/4 plus 1/8, 7/8. And then what do I get when it's 4? I get 1/2 plus 1/4 plus 1/8 plus 1/16. I think that's 15/16. Okay, and then what do I get when I add up 5 of them? 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. I'm pretty sure that's 31 32nds. You can check with a pencil. I already did. That's how I know it. It's not like I can add those up in my head that fast. Okay? All right, so then what would happen as n goes to infinity? Well, we could certainly look at all these dots, all these sums. So the sums would be n and s sub n. These are all the sums. So before, we were looking at the terms. Here are the terms going down. Now what I want to look at are the sums. So look at what the sums are doing. They're going up. In fact, they seem to be leveling off. In fact, if I let n go to infinity, what does it look like it might be getting closer to?
1.
1. And so we would say, and there's a couple ways to check, right? We could just put in a great big number like this. Ooh, let's do that. And of course, Desmos says that's close enough to 1, I'm going to round it off. And if you get a little shorter than that, then we seem to be getting closer to 1. So now we're interested in adding up a bunch of terms. Sometimes when we add up the terms, the sum goes off to infinity. And sometimes when we add up a bunch of terms, it goes to a number. In this case, it goes to a number, right? And it turns out that that's a little bit more interesting than running off to infinity. In fact, it's a lot more interesting than running off to infinity. And it turns out that this happens a lot. Okay, maybe you haven't run into it yet in your other studies, in your other classes, but adding up a bunch of terms of the sequence seems to be a fairly big deal when it comes to having a mathematical tool to solve a problem that comes up in business and chemistry and finance and lots of places. So we are going to consider this for a while. What happens when I add up a bunch of terms of a sequence? First of all, we're going to say that when we add up a bunch of terms of a sequence, we call it a series. And what we want to know is, what's the sum of the series, right? What does the series converge to, if it in fact does converge? And then we're going to consider a bunch of these and see where they go. That is our plan. So the rest are examples. And then I'm basically done. And then you go look at some examples and see if you can figure out where they're going. Let me give you a couple, and we'll try a couple together. And then I'm going to let you go. I'm going to let you go find a bunch, because I just have like do problem number 17, 18, 19, 25, 30 right from the homework. That's what my notes say. So here's another example. Okay, so we said this one goes where? 1, right?
Would you mind if you show your Desmos real quick again for that last problem?
Be happy to put Desmos back up. So here's the formula for the terms of the sequence, and here's the formula for the partial sums, right? This is the formula for the partial sums.
Cool. Thank you.
And you can graph them both on the same window, but sometimes they don't fit real well because, not that, this, right? Because look at what's happening. The terms of the sequence are getting smaller, but the terms of the sum are getting bigger. And depending on what they go to, maybe they both fit in the same window nicer, sometimes they don't. So sometimes you have to do those sort of individually. Okay, let's try another example.
Thank you.
You bet. Here is another example. Let's do this one. I don't know, let's just do this one. The sum of I equals 1 to infinity of 2i over 3i plus 5. Now, one thing that I might point out, and this is why I've been struggling a little bit, we used i's going to n, right? Where n was where we stopped. When we saw this before, back when we were doing Riemann sums, we used I all the time for our index. What Stuart does in this section is he uses n for his index. Okay, he uses n for his index because he doesn't need a place to stop, because he's going to go all the way to infinity. So what you're going to see in the book is that it's going to be written n equals 1 to infinity of 2n over 3n plus 5, like this. So now n is starting at 1 and going to infinity instead of I. And since we're not stopping, we don't need to put a place like an n up here that we're going to stop. But if you want to write this as a limit, now you have to say the limit, and you have to say, you know, something is going to infinity. The upper end point is going to infinity, but you already used n now. So you can't say n is going to infinity if n is also going from 1 to infinity, right? 1 to n. So you're going to need a new letter for right here. And I think the last time we did this with indefinite integrals, we used a t, right? So maybe it would be better to put a t in here. But a t sounds like a real number. So really t is not a good number to put in there, because t would suggest it's a real number, and what we really want is an integer in there. So then I would say, well, use big N, because big N sounds like a nice place to stop. But big N we used in Desmos to represent a list of numbers, an array of numbers. So what I might use, I don't know, in our bounded theorem, we said to some maximum value, m, right? And then you could say as the maximum value goes to infinity. It doesn't matter what letters you use here. It just, so long as you don't confuse yourself on what's going on, right? I think you're going to see this notation in the book most of the time. All right, so let's figure out where this thing's going. We got the sum n equals 1 to infinity of 2n over 3n plus 5. And so then the question is, what's it doing? And you'd say, I don't know, what's it doing? So you'd have to maybe list a few terms. That's the first thing I would do. So put in 1. You get what? 2 over 8. That's the first term. And then you put in 2, and you get 4 over 11. And then you put in 3, and you get 6 over 9 and 5, 14. Okay, and then you put in 4, you get 8 over 12 and 5, 17. And maybe that's enough, or maybe you need a lot more. Okay, but so far all we did is we took this notation in sort of sigma notation, compact form, and we just wrote it out the long way. And I think that that's pretty helpful. That was helpful when we were doing Riemann sums a long time ago. And so what are these terms doing? Are they getting bigger? Because if they're getting bigger and I'm adding something bigger onto my sum, then I have a feeling that this is going to run off to infinity. Does that make sense? So if we have any chance or any hope of this series converging, then the terms themselves had better be getting smaller and smaller and smaller. So what do you think of these terms? Are they getting smaller?
No.
I don't know, it's hard for me to tell without a comment. That's why I always go to Desmos real quick, right? Because I can't tell, you know, this is a quarter. So is this bigger than a quarter or less than a quarter?
It's bigger.
That's bigger than a quarter. Uh-oh, this is bigger than that. 4/11ths. 4/11ths is 3, 6, 3, 6, 3, 6. And
Yeah.
6/14ths, that's bigger than that, isn't it? These terms are getting bigger. So what do you think is going to happen with this? I'm thinking it's going to diverge. Okay, so how would we check? I don't know. It's easier to see them if you're looking maybe at the decimal expansions of these, or it's a heck of a lot easier if you just look at Desmos and see where they're going. So we would say, what are the terms of our sequence? The terms were 2n over 3n plus 5. So the terms are green. Yeah, you got it? Terms are green. The sums are red. So the terms themselves seem to be leveling off. In fact, we know the limit of this sequence. What's it going to?
I think it's going to roughly, would that be 2/5?
Close.
No,
The
it's
other
not
way.
2/5.
Divide by the highest power of the variable in the denominator. 5 over
Oh,
n goes
2/3.
2/3. Yeah, this goes to 2/3. Okay, so these terms are going to 2/3. So what's the sum going to? Well, what if I added up like infinitely many 2/3? What would I get?
Infinity.
Infinity. There they go. Up to infinity. So if the sum is going to go to a number, then the terms are going to have to get smaller. They can't get bigger. So this one diverged. All right, fine. Let's do a different one. Ready? We want the terms to be getting smaller. So maybe I make it 3n squared plus 5 in the bottom. Now what are my terms doing? Now my terms are definitely going to 0, yes? Green are the terms, red are the sums. So it looks to me like the terms are getting smaller, 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 smaller. The question is, what are the sums doing? Well, so far it looks like they're getting bigger, but it looks like they're starting to level off. Are these going to level off, keep bending and have an asymptote? Or are these going to keep going up the way they look like they're going, just slower and slower and slower, right? Are they still going to go up? Or are these going to bend and level off? It's really hard to tell from this picture, isn't it? So what's the answer? I don't know what the answer is. We have to do some math to prove it because the picture isn't enough info. Now, one way we can get around this, of course, is we can put more terms in here. Let's go out, say, 500 terms, 5,000 terms. Whoops, Desmos can't handle 5,000. Okay, 500 terms. I still can't tell because my red dots, at least from Desmos, look like they're still going up and haven't really leveled off yet. Are they going to level off way out there around 1 million terms? Or are these going to keep growing slowly, slowly, slowly growing? This is going to be a hard one to tell, and we're going to have to do some math. Right? We're going to have to actually prove it using something other than it looks like it. And I don't know if I'm ready to do that yet. So I'm going to leave that one as a question for you, since I just made up the problem. What if I did this, though? What if I put cubed in here? Then the terms are certainly going down. The red ones are certainly going up, but they sure look like they're leveling off now to me. In fact, if we put in some big sums, we could say the 100th sum is 0.638. The 1,000th sum, 0.644. Uh-oh, 645. Uh-oh, 6452. 64521. Does that look like it might be leveling off? I mean, it's a lot of terms. What's that? That's 10 million terms. But it looks like it's getting closer to somewhere around 0.64521, right? Do another one, 6452, it didn't change. So it looks to me like it is leveling off, but it's leveling off somewhere out around 100 million terms or so. So now I would say we have stronger evidence that in fact this sum is converging, but it's converging to kind of a weird number that I don't recognize. And I'm not 100% sure yet. So how do I prove it? Okay, well, that's all the rest of chapter 11. The rest of chapter 11 is how do I prove this is actually going to a number kind of close to 0.645211 something, something, something. And so I can't answer that today because it's the whole rest of the entire chapter. Right? But we're going to get started, right? And the way we're going to start is you are going to just investigate a few. So just like when we started limits a long time ago, the very first step is guess. Guess what you think it's going to. And then provide some evidence. Like what kind of evidence? Like a table and a picture in Desmos, okay, to support your guess. And then eventually, like Monday, we're going to decide that a picture, it looks like it is not strong enough, and we're going to try to develop some other tools, right? Some other arguments for stronger arguments for why we say it's going where it's going, right? That's kind of our plan. And then there are up through 11.7. So there's like 6 sections of the book that develop stronger and stronger arguments for why it's going where we say it's going. And we're going to look at a few of those sections, as many as we can squeeze in. And then we're going to leave the rest for you to explore when you have more time. Okay, so that's kind of the plan. Questions about what we're doing? I'm getting no. A couple of no's that I could see shaking their heads. And the rest of you that are not on video, if you don't write in like in the next 10 seconds, I'm going to just let you go. And if you have questions, you can ask me at 10, or you can write me an email over the weekend or see me on Monday.
Sure.
Okay, all right, give those a try and we will see you on Monday. If you didn't turn in your take-home part, do so please by midnight tonight so that I have something to do on the weekend. Katie.
I actually have one question.
Okay.
So we should be able to do most of 11.2 or all of it?
I would think pretty much all of it. We went a little beyond. Mostly 11.2 is just investigate where these things are going. And then when we get into 11.3, we're going to write stronger arguments. Okay?
Okay.
All right. You guys have a great weekend. Stay safe, stay healthy, and we'll see you on Monday.
Quick question, actually. Sorry.
No worries.
It looked like the due date on Part B was on the 12th.
Oh, was
I was
it?
just wanting to
Oh, I
double
thought
check
I
that.
made it Friday. If I didn't make it until Sunday night, that's fine too. Yeah, take the
Okay.
weekend. It wasn't supposed to be a time thing, and I wanted to give you enough time that in case you had work or, COVID issues or whatever, or connection issues, that you'd have plenty of time to get it done. So yeah, anytime by Sunday, that's fine. If that's what I posted, go ahead and take till Sunday.
All right. Thanks. Have a
You
good
bet.
weekend.